Okay, so we're going to go over 6.8, which is called relationships with meaning. And it's called solidifying understanding, meaning we're still in the exploring kind of stages and we haven't gotten to the practice part yet. So it means that you shouldn't necessarily feel completely lost, but you also shouldn't be comfortable enough to be like, oh my gosh, Miss Johnson, this is so easy, right? So you're in that kind of like middle stage. All right, so today you'll be able to examine properties of trig expressions. Okay, and what observations can I make about relationships between trig ratios, meaning sine, cosine, tangent, of the two different reference angles in a right triangle, meaning not the right angle, but the other two angles? And how do the properties of a right triangle influence algebraic statements involving trig expressions? So if those questions don't even make sense to you, don't worry. Just make sure that you're comfortable with what we are talk about today. So it says, number one, it says the sine ratio of 30 degrees for a 30-degree angle is 0.5. So I'm just going to tell you right now, whenever I see decimals and I'm dealing with this, I will always switch it over to a fraction, because sine is opposite over hypotenuse, and it's a lot easier to deal with if I see a fraction. So the very first thing I'm going to do is I'm going to change this guy to 1/2, because then this guy's my opposite and this guy's my hypotenuse, and everybody like kind of has a place. We write this as sine 30, and the way we say it is sine of 30 equals 1/2. And again, I'm going to write this as 1/2. Use this information to find the missing sides of the right triangle. So when we say it's a ratio, and if you remember ratios from like 6th and 7th grade, it means for every one part, there's two parts. Okay, so let's just say I have stars, and then I have, I don't know, circles. Okay, so the ratio of stars to circles is 1/2, meaning for every one star, there's two circles. So for every one star, there's two circles. Does that make sense? It does not mean there is one star and two circles. So sometimes when you need to look at this, I write this as x over 2x. And that's actually how I'm going to use this to solve this. So the sine ratio of 30 degrees is opposite over hypotenuse. And I said I was going to write it as x over 2x. So the opposite is x, and the hypotenuse is 2x. But Ms. Johnson, it says it's 8. Good. Now solve for x. So since 2x, two of the parts equals to 8, that means x equals to 4 if you divide out. So that means this is 4. Okay. So now that you know that, now you can solve for the third one by using the Pythagorean theorem. Now, I will tell you right now, the 30, 60, 90 triangle is it is a staple in trig. So as soon as you find this, make sure that you keep this in your head. This should be as known as times tables was back in 3rd, 4th, and 5th grade. Okay, so I'm going to use the Pythagorean theorem to solve this. So I'm going to go 4 squared plus, I'm going to call this b, plus b squared equals to 8 squared. So then this is 16 plus b squared equals to 64. And then I'm going to subtract 16, subtract 16. So I get b squared equals to 48. And then I'm going to take the square root of it. And then we're going to say b is equal to plus or minus. 48 is 12 times 4. And this is 3 times 4. And so if I'm looking for pairs, I have a pair of 4s right there. So that's 4 root 3. Now, sometimes I go down even further and go 4 is 2 times 2. and 4 is 2 times 2. But if I see a pair, then I'm gonna pair them up earlier rather than doing all that work. Now I'm gonna cross off my negative because we're talking about the side length of a triangle. So in this case, it's 4 root 3. Now I'm gonna be honest with you. Later on in the land of your next math class, it might be that I use that negative and write it out as a side of a triangle on the coordinate plane. But as it sits right now, I'm only going to use the positive side. Make sense? So this triangle here, he's famous. His ratio of the sides will always be the same. Okay. It says you can find the values of the trigonometric ratios on a scientific calculator. Find the cosine and sine for 50 degrees on a calculator. So I'm going to show you, if you use Desmos, there's something that you always have to do to make sure that you're going to get the right answer. Otherwise, it's going to look like you got an answer and it looks right, but it's actually wrong. Sorry, I'm clearing out all the stuff that I used today. Okay, so they want me to find the cosine of 50 degrees. So the very first thing is I push cosine. You can actually type it if you want. And I'm going to put 50. The thing that you have to check, and I'm going to say this over and over again, and you're going to be like, Ms. Johnson, don't forget to change the degrees. So I'm going to say this over and over again. Make sure that your calculator is in degree mode. Now, if you're not using Desmos and you're using like a calculator that you'll hold in your hand, it'll either say DEG or D or R or RAD somewhere. You want it to say D or DEG. Okay, so that's degrees. Oops, did I hit degrees? Cosine of 50. Okay, I did. Sorry. So the cosine of 50 degrees is 0.64. Now, notice here when I hit radians, it's a different number. And the calculator is like going to give you an answer, and you can't tell if that answer is correct. So just always verify that you're in the right mode. So it's 0.64. Okay, so this is about 0.64. And just depends on how many digits you want to take. The more digits you take, the more precise you're being. But for right now, I'm just going to grab the first two. And I'm going to find the sine of 50. Sine of 50. And I don't need to change it because I already know that I just used it. So 0.77. Now, Ms. Johnson, you said that you like to write your sine in fraction form. How come you didn't write it here? Because it came off the calculator. And if I put it in a fraction, then just leave it as a decimal for now. Okay. So I will say, for the most part, you'll see me using a lot of fractions. So it says, use this information to find both the missing sides in the right triangle. Okay. So here we remember that cosine is 0.64, which is adjacent over hypotenuse. And you're like, Ms. Johnson, it doesn't have an hypotenuse. It's okay. It's a 1. So then because we want to have these as multipliers, I'm also going to put x's on these. Okay, so I shouldn't have actually done it here. So I'm going to write this as 0.64x over 1x. So I'm going to go over here and write 50 degrees is adjacent, Ms. Johnson. 0.64x equals 1x. And the hypotenuse is 1x. So this is the hypotenuse here. This is the hypotenuse. I'm just matching them up. Here's my adjacent side here. And then same thing goes here. I'm just going to put this over 1. So this is going to be 0.77x. And then I'm going to solve the equation, and then I'm going to plug in my x's to each of those, and then that's going to be my answer. So it says x is equal to 12. So now I'm just going to plug in 12 here and write it out. Okay. So I'm going to go 0.64x, which is 12 in this case, oops, times 12. So I got 7.68. So this is about 7.68. And I'm going to do the same thing to the other thing. I'm going to go 0.77, oops, 0.77 times 12. And I got, this is about 9.24. Okay. So there you go. You found the sides. One way to verify that you're correct is by using the Pythagorean theorem. So I'm going to do that really quick. I'm going to go 7.68 squared plus 9.24 squared. That's 144.36. And then I'm going to square 12. And it's 144. So some of people are like, Ms. Johnson, they're not exactly the same. They're not, because when I came up here, remember, I didn't take all those digits. I didn't take all those. If I did take all those digits, that difference between 144.36 and 144 would be a lot closer. It'd be a lot smaller of a difference, right? So then it says, use your calculator to find the information you need in order to find the desired side in the following right triangles. Record all of your work, including the trig ratios you used. So right now, what I want you to do is I want you to look at number 3. And it says, find the adjacent side of 75 degrees. So they want you to find this. So the first thing that you're going to do is you're going to write a trig equation or trig ratio, sine, cosine, or tangent that I can actually use to find that side. Okay, so the first one I'm going to try, and this is, I already know how to do this, but I'm going to pretend that I'm you. The first one I'm going to try is sine of 75 degrees equals to, and then this is, I don't know, over 10, which doesn't help me because I want the x. I don't want the I don't know. Does that make sense? So I can't, sine is not going to help me. Darn. So the next one I'm going to use is I'm going to try cosine. So I'm going to go cosine of 75 degrees. And if you remember cosine is adjacent. So this is x over 10. And you're like, yes, that's it. I need to do that. So then before I plug this into my calculator, I just want to talk about solving for x. Solving for x before today and solving for x today is exactly the same. So how do you undo dividing by 10? How do you inverse dividing by 10? And you guys are like, oh, just multiply by 10, Ms. Johnson. Very good. So I'm going to pop that 10 out all the way out in front. Do not put him behind because then you might get confused. Are we multiplying 75 times 10 and then we take the cosine of it? Here it's very clear. You take the cosine of 75 and then you multiply by 10. And that's actually exactly how you'll enter into the calculator. So let me write that out. X is equal to 10 cosine 75 degrees. So I'm going to enter that into my calculator. 10 cosine 75. What do we always have to check, people? Yes, very good. We have to check if our calculator is in degree mode, which it is. So it's about 2.59. So this is about 2.59. So this is about 2.59. Okay. And that kind of makes sense because number one, this angle looks really little. This angle here, I'm going to call him theta, is really little. And this short side should be way shorter than your hypotenuse. Now, if I had gotten 25, the little red flags in your head should be going off because how is the leg of a right triangle longer than the hypotenuse? It doesn't work like that, right? Okay, I want you to try doing B and then pause the video and then come back to me when you're ready. Try finding B. They want you to find the opposite side of this. So just in case you're wondering, remember we talked about opposite going this way. So the opposite side is going from the angle across the triangle. So we're looking for this side here, which I will call I'll call him H for right now. So go ahead and pause the video, write your equation, solve the equation, check back here. Okay, now that you're back, we're going to write some equations. Now, some of you are getting in tune to this and you're like, it's not going to be sine because I don't know the hypotenuse. And that means it can't be cosine because I don't want to involve the hypotenuse. So it has to be tangent, right? So either you're going at it from the like sine is height and uses hypotenuse, or you're going about it the opposite direction. No pun intended. Because they gave you the opposite and they gave you adjacent. So you're thinking, okay, which one of those sine, cosine, or tangent involves opposite and adjacent? And you're like, oh, it's tangent. So there's a couple different ways for you to go figure out which way you like better and then use that way. So the tangent of 35 degrees is opposite, which is h over 10. And then so I'm going to tell you the same thing again. So how would you solve this? How would you get rid of the divided by 10? And you're like, oh, use the inverse. So we multiply by 10. Make sure that you pop the 10 all the way out in front of tangent, right? And so therefore h is equal to 10 tangent of 35 degrees, right? And then I grab over here on my calculator and I go 10 tangent of 35 degrees, making sure that I'm using degree mode. So I am. So it's about 7. So I'm going to say h is approximately 7. So I'll put 7 here, and there's your answer. Okay. So there's, again, 2 ways to go about this. Either you're thinking these are the sides they gave me, which sine, cosine, or tangent is it? Or going through like a laundry list. Can I use sine here? No, because it's hypotenuse. Oh, that means I can't use cosine, kind of thing. All right, this one, it says find the hypotenuse. So I'm going to put C here. So obviously, because I want to find the hypotenuse, right? Oh, sorry, go ahead and pause this and figure it out on your own and then come back to me when you're ready. Okay, so now that you're back, again, there's 2 ways to go about this. They gave me the hypotenuse and they gave me which side? Which side did they give me? Maybe you're like, oh, Ms. Johnson, they gave me the opposite side. Very good. So they gave me opposite and hypotenuse. So which function is that? Is that sine, cosine, or tangent? Very good. You said sine. So it's sine of 48 degrees equals to 8 over c. Excuse me. Now this one's a little different because your c is in the denominator. And so I've told you guys before, whenever I have denominators in equations, I multiply by the common denominator. So nothing changes. I'm still going to multiply them here. So then this goes away. So I have c sine 48 equals to 8. And then how do you get rid of that? How do you get c by itself? Well, I just divide by sine of 48. Oops. So c is equal to 8 over sine 48, which should feel a little weird. You're like, Ms. Johnson, I didn't know we could divide by sine 48. It's a number, so of course you can, right? So I'm going to go on my calculator, and I'm going to go 8 divided by sine of 48. And this is the reason why I like Desmos so much, is because the way it looks in the calculator is the way it looks like right here, right? It looks exactly the same. Right? Mine is cuter, obviously, because I have cute colors and cuter writing than that type. I'm just kidding. Okay, so then it's about 10.77. So C is about 10.77, which kind of makes sense to me because that's bigger than that side, right? So yeah, that kind of makes sense. Okay, now it says, use the following information from the given triangle to write the following trig ratios. So this is something that you guys know how to do. So I'm going to skip over this and you guys can check your answers with me tomorrow. This one says, use the given information from the given triangle to write the following trig ratios. And now we have a blank. So they just are testing you here can you do it even if it's ratios? So, or variables as your sides? And the answer is yes. So I'll do the first one with you. The sine of A is going to be A over C because it's opposite over hypotenuse. And just a little note here, just in general, whenever we draw a triangle and we have missing sides, sometimes what we do to make things very clear is the side opposite of the angle are going to be labeled the same letter, except for angles are always going to be labeled with a capital letter because it represents a point, versus the side length is going to be labeled as a lowercase letter because it represents a length. Okay, so notice A is across A, B is across B, like that. That's what I'm saying. Okay, so go ahead and finish all of these, and then you can check back with your answers. Okay, so then your answers should be cosine of A is going to be B over C, and then tangent of A is A over B. For sine of B, it's going to be B over C. Cosine of B is going to be A over C. And tangent of B is going to be B over A. Okay, so there's your answers. It says use the information from the previous two problems to write observations you note about the relationship between the trig ratios of the two different reference angles. So this is something that you guys have already noticed. I said, what do you guys notice? And I was only looking at sine and cosine. I said, hey, what do you guys notice? And you guys talked about this, like how cosine of A matches with sine of B, and that sine of A matches with cosine of B. There's like some switching happening going on. Does that make sense? I think that's the word that you guys use. And then same thing kind of with tangent. Tangent, they're using, it's almost like a different kind of switching. Okay. And then they say, do you think these will always work? And we talked about that as well. And it makes sense because we had talked about, if I remember correctly, when I look at A's opposite, that's this side right here, right? But A's opposite is B's adjacent. So that's why it makes sense that they'll switch like that, right? So then the following is a list of conjectures made by students about right triangles and trig relationships. For each one, state whether you think the conjecture is true or false. Is true or false. So this first one, what do you think? Is cosine the same as sine? Do you think cosine and sine are the same? Right? And so for some of this, it doesn't make sense because you're like, well, no, because like these two numbers are different. And if you look at your answers over here, yeah, that guy's opposite is not that guy's, it's not the same. So I will say this is true. I mean, this is false most of the time. I'm going to let you guys think about when would it be the same? Okay, tangent equals to sine over cosine. Tangent equals to sine over cosine. So that's that's A over C over B over C. And if you remember, when you divide by a fraction, you multiply by the reciprocal, right? It is A over B. I wonder if that's always true. And then sine of A equals cosine of 90 minus 8. This might make sense to some of you because of that relationship between big A, angle A, and angle B, and how they're related. And so the answer here for that one is yeah, because when you look at 90 minus A, you get B. So if I'm looking at I forgot what it was. if I'm looking at the sine of A, you told me that the sine of A matches with the cosine of B, and 90 minus A is B. So yeah, that makes sense, right? So I want you to go through these couple of ones here and see if those ones are true. And then we are going to check back together on those. And some of them, it'll make sense and some of them won't. So something that you have to learn, that when we say sine squared, it actually means this. So, oops, sorry, I was supposed to highlight. Okay, so sine of A, when we square that, we actually write it as sine squared A. So I also want you to kind of look at these ones to see if these are true. Okay. Okay, and then I want to show you your takeaways. Give me 1 second. Okay, so I wanted to go over your takeaways and make sure everybody's comfortable. So when given the measure of an acute angle and one side of a triangle, we find the others by deciding which trig ratio we should use. Remember, we were talking about sine, cosine, or tangent, and the side that we're trying to find. So finding the value of the selected trig ratio for the given angle, writing an equation involving the value of the trig ratio of the given angle and the ratio sides, and solving the equation for the missing side. Okay. Okay. An identity is an algebraic equation which is true for all replacements of the variables. When working with trig ratios, some surprising results occur. The following trig identities capture some of the observations we made today. And I want you to write down some of the ones from the previous slides here, like maybe with some of these that actually made sense, and we'll check on them when we get to class tomorrow. Thanks for listening. Have a great day.